So hello everyone. Maybe I'll just wait for a couple of minutes because I see only 7 here, but we're expecting 10 in addition to me. So maybe a couple of minutes and then we will start.
Sounds good.
So I guess you guys hear me, correct? So can someone confirm that you hear me? Because I see that Mohammed said he does not hear. So okay, thanks. Okay, maybe one more minute and then we can start. So if it's convenient, I would be more than happy to see you in the first lecture. It's a small class and it's good to know all of you. So if you don't mind, if it's okay, I would be happy at least in the first lecture to see your faces, to kind of get to know you. I guess my starting would be that everyone introduces himself. Okay, we became 9, so I guess we are only missing a single person. Thanks, Ryan. Thanks. So I would say maybe we can start now. It's already enough, and then if someone comes later, it would be okay. It's already 2:03. Okay, so given that Ryan, you are the first one who took the initiative, so I would be more than happy if you start introducing yourself. It's like just a couple of sentences everyone can do to get to know you better. What is your area of work? Whom are you working with? Why you take this course? What you might expect?
Yeah, sure. Okay, so hi everyone. My name's Ryan. So I'm working with Dr. Nicolici, specifically in the area of kind of like post-silicon validation and verification in general. I'm actually a part-time student, so I work full-time at Synopsys doing pre-silicon verification. And then besides that, I mean, I took this course because I'm interested in learning more about computer architecture and real-time systems.
Perfect. Thank you so much. I guess Mohammed, you can go next if you'd like.
Yeah, sure. Okay, hi everyone. I think we know all of us like from Dr. Nicolici's course, so it's nice to see you all again. I'm Muhammad. I'm working with Dr. Muhammad Hassan actually, and I'm working in caches and memory architectures for different systems. So this is mainly what I'm working in, and also I was like a digital design engineer back in Egypt for 3 years. So this is all, and it's a pleasure to see you all again.
Thank you. So someone to go next? Salah, would you like to go?
Yes, sure. So hello everyone. My name is Salah Hussein. I'm a master student in electrical and computer engineering. So I work mainly on digital hardware design and embedded system in my research work with, of course, with Professor Muhammad Hassan. And yeah, I joined the McMaster last winter, 2010. Yeah. Thank you.
Thanks. Someone to volunteer, or should I back? Zen Tan, would you like to go next?
Yep, sure. Hello, my name is Zeng Tan, and I'm also one of the ECE student. I'm an MEng student, and this is my first year. So I think like architecture is very important for programming, so that's why I joined here.
Perfect. So are you joining the MEng program remotely, Zen, or you are here in Canada?
Oh, I'm here in Canada actually.
Okay, perfect. Okay,
Thank you.
good. Thanks. John, would you like to go? I guess John just joined, so maybe Hongi Lee. Hongi, this is how you pronounce your name?
Yes.
Okay, perfect.
My name is Hongi Lee. I'm a Master of Engineering student of ECE, and I did some analog circuit design before.
So, Hongi, whom are you working with? Who is your supervisor?
I don't have a supervisor. I'm a Master of Engineering student.
Oh, an MEng student. I see. Okay, perfect. Is this your first semester or?
Second year.
Second year. Okay. Yeah. All the best with the program. Thank you so much. Then, John, you can go if you wish.
Hi, everyone. So my name is John. I'm currently a... Oh, here I am. Perfect.
Hey, nice seeing you.
Hello. So I'm currently a PhD student under the supervision of Dr. Ahmadi. And I'm in the electrical computer engineering stream. And currently I'm working on solid state power controllers. And ideally, I've got some experience in FPGAs and multi-core controllers. So this is why I thought this would be a good opportunity to take this course.
Good, perfect. Thank you so much.
Thank you.
Teresa, would you like to go next?
Sure. So I'm a second year MEng student in ECE as well. And so I'm just interested in learning more about embedded systems and real-time operating systems.
Perfect. Thank you so much. I guess we all went through. Okay, perfect. Maybe I'm last. So I'm Muhammad Hassan. I'm a professor here at McMaster University ECE department. I do work in computer architecture and cyber physical systems. This is the first offering of this course, so I hope we kind of all enjoy the journey. As we will see, I will share with you my expertise in the field. I would also be more than happy to hear from you how to apply what we learn into your specific field. So let me start with sharing some slides with you. Something to mention is I have already uploaded the first two slides, what I usually call lecture 0 and then lecture 1 on Avenue to Learn, where I'm going to upload all the slides there. So I usually upload them before the start of the lecture for those who would like to take notes. The other thing is I will do my best to make sure I record all the lectures, but please don't. So I would say this doesn't mean you don't attend the lecture, because it would be more of an interactive nature. And as we will see, we have some lab assignments and presentations and the project. So it's good to be in the lecture to discuss stuff, right? So before delving into what is even this course about, I usually start any course I teach with this bigger picture. What is computer engineering in general? Given that this is a grad course and you are all experienced engineers, it might be not very new information, but it might be good to refresh our minds and consolidate the knowledge. And if you want to add anything, please jump in at any time and ask questions, add notes, and stem a discussion. I'm more than happy to do that. Good. So looking into the full system stack of computer engineering. So we start from the software level. So we have the application layer. This application includes software development, algorithms, etc. And then once you have an application, this application goes through a compiler, which might include a compiler, an assembler, a linker. And then once you come up with an executable, you should run this on top of a platform. This platform, most of the time, would have an operating system. You can still, in some embedded domains or automotive domains, to run in what we call a bare metal environment, where you don't have an operating system, or you only have a kernel, but generally you have some form of an operating system. So in the operating system, as we will see as part of this course, we have in embedded systems what we call real-time operating systems, or RTOS, which is a special type of operating systems. But in general, the main function of the operating system is to handle different running applications. You do scheduling, you make sure the application gets the sufficient memory, and sometimes you switch between different applications based on priorities or different scheduling mechanisms, as we will see. So you have a scheduler, loader, maybe device drivers if you have multiple input outputs. All of this is still within the software layer. So sometimes, and this is a field of its own. In fact, each box here is someone can have his own specialized field in industry or in even in research as one of these boxes, right? But this is the bigger picture that I always want to emphasize. After this software is running not just in the thin air, right? It runs on top of a hardware. So we have what we call the contract between the software and the hardware, which is the instruction set architecture. ISA is nothing other than a document that is released by the processor manufacturer, or the one that came generally by this instruction set, that tells you how to write programs, or in this case, compilers, such that they satisfy certain contract terms. So ISA, if you open any ISA document, you would see this, like it tells you how to do addition, subtraction. So it's a form of a contract that communicates between the software and the hardware. Can I ask what forms of ISA you are aware of? Can someone name like an ISA that he knows about?
RISC-V.
RISC-V, perfect. Yeah, that's one of the newest ones, and maybe there is a lot of ongoing work on that. So RISC version 5 is one of the ISAs, that's correct. Anyone else bringing some?
Intel 18's family.
Yeah, x86, correct. So x86 is the Intel instruction set. There is also ARM, right? In your mobile phones, most of them are ARM, either ARM version 8 or version 9 instruction set, right? There is also the Power BC instruction set for, I guess it might be in your Xbox or some machines that have the Power hardware from IBM. Good. So these are some good examples of the most common ones are the ARM ISA because of the prevalence of mobile phones and embedded devices, and x86 from Intel because of the desktop machines and servers. Good. So ISA, if it happened at any time and you open these documents, and they are available online, right? So you will find it's just a contract that tells you what to do at each step, how an addition is executed, what maybe some of the flags that you need to trigger in the hardware, and how to read them. So think of this always as this. You have a contract between the software and the hardware. So great. So at the end, any program gets transformed into these instructions. And then they execute on top of the hardware. Hardware here means many, many things. And like every one of you might be working on a different stack or different level of these. At the top level, we have the computer architecture. So we have the processor architecture, memory system architecture, maybe input-output devices. But also the level below the computer architecture, we have what we call computer organization, how the processor itself is being implemented in a little bit more details. The more or the deeper you go, the more details you have. For example, a processor would have a data path and a control path, which is usually covered in a computer organization undergrad course. And then this would be somehow high level, decoders, encoders, multiplexers. So it talks about the digital design in the high level, right? And then going lower, you would have the digital logic design. For example, how these bigger blocks are really composed of, I mean, at the end, you have gates. right? Then those gates would, on the other hand, be composed of MOSFET transistors, right? So at the end, everything goes back to that you have, your design unit is just a transistor, right? And here we have some experts from the pre-silicon, post-silicon. So it's, you guys are kind of aware of these details here, right? And different companies, in fact, work on different levels based on how far you go. So IC layout design, dealing with wafers, how like the transistor width, length, dimensions, etc. And then how you construct different circuits from transistors, logic gates, for example. And then you would have some net list of these gates where using some tools like Design Compiler or Cadence IC, that you take the design and then at the end synthesize it into a specific logic gate library, right? Good. So looking into this from a different perspective, you would see that what I would call a journey of a program, right? So we can look into the stream of computer engineering also in a different way. Is you write some source code in any language, it doesn't really matter. And then this source code gets compiled using a compiler. Again, what compiler doesn't really matter. It can be LLVM, GCC, any other compiler. You get an executable. The executable runs on top of an operating system. Again, here we have many: iOS, Windows, Linux, Android, etc. And then by the compilation and the execution process, everything gets translated into assembly, instruction set, and then machine code. And then the machine code is executing on top of a hardware platform, right? So with some other details, for example, you don't start really from, if someone in an application level, you don't start from writing source code. This is in fact not the right way. The right way is you have a specific real problem, whether this is your own problem or a problem from a user, and you want to develop an algorithm that's efficiently solve this problem. And the way you write this algorithm is in some programming language. This is the implementation. So think of any course you have taken in your undergrad or even your grad. You would find that they fall in one of these kind of categories, right? Thinking even in AI, machine learning, or algorithms, data structures, software engineering, all rely in this box, right? So you are discussing some form of algorithm to achieve a certain target, right? And then how do we implement this algorithm? We have what we call programming courses, software development courses, and it's in this category, right? And then here we have compiler courses. I don't think here in ECE we offer compiler courses either in undergrad or grad programs, but other ECE programs do. And I guess also CES offers some compiler courses, but usually you find two different courses in this category: compiler construction and compiler optimization. And this is a research field on its own. And in fact, there are many teams in industries that only works in compilers, right? Then afterwards, you have the operating system. And again, this is a topic on its own. There are usually undergrad courses that only for operating systems. Here, as part of this course, we would talk about real-time operating systems. And then talking about the architecture, we have the computer architecture and the organization courses. And then going lower level, beneath the architecture, we have what we call computer organization, data path and control design. For example, designing ALUs, control unit, fetch unit, etc. And then going deeply into this, we have what we call computer arithmetic, right? Everything at the end is composed of some digital logic design. Like here we have this ALU, looking into the ALU, how it's getting translated by a software netlist. You would find some gates there, right? And then lower, as I mentioned, everything is just consisting of transistors. Like this is be an AND gate, an inverter, and NOR gate. You would have transistors at the end. And the topics that cover this is circuit design, electronics, physical design, digital design. Good. Okay, so before going here, is there any question or anyone wants to add anything? Nope. Okay, so good. So the other thing is you can think of, we might have covered this in only talking about like desktops or laptops or processors for these machines. But in fact, the revolution we have right now in many of the embedded systems like IoT, wearable devices, smartwatches, or before this, mobile phones. They are almost exactly the same thing, but in a different format, right? So here I'm comparing a laptop with a mobile phone, but you can, as I said, do any other thing, like an IoT device. In fact, you can do a self-driving car, because currently they depend on electronics. They have sensors, cameras, which are mainly input devices, and then also you have processing units to handle this, and then you have actuators to take an action, right? So everything can almost be aligned on the bigger picture. Comparing the laptop here with the mobile phone, you have input-output devices. This can be in a form of a monitor as an output device, or a screen, and then a keyboard or a mouse as an input device. Looking into the phone, you have a touch screen, which is in fact can be considered as both input and output device at the same time. And then inside your laptop, you would have a motherboard that holds processor, memory, and other devices, or accelerators like a GPU, for example. Exactly the same thing in your mobile phone. You have a board that has usually a system on a chip, for example, like Qualcomm Snapdragon system on a chip, where you have a CPU, a GPU, memory, camera modules, Wi-Fi modules, and other things like audio interface, right? So at the end, you can think, if you abstract your knowledge, you can apply it to any field. And as we will see throughout this course, all the concepts we cover, we can touch in automotive as an example, and here we have people from Dr. Imadi's group. We can also touch in IoT, we can touch in like electronics, we can touch in mobile phone design. So really the application doesn't matter, the concepts would remain the same. Okay, so is there any questions so far? We are good? Okay, so let's then, after this bigger picture, let's look into what is this course about, right? So thinking of embedded systems, in fact, if we define them, we can kind of a little bit vaguely define them as computing systems designed for a specific purpose. So why we say this? Because by defining or defining them in this way, you take away the general purpose computing systems. Like, for example, your laptop. Your laptop cannot be considered as an embedded system because you cannot plug in your laptop in a washing machine, for example, right? So an embedded system is like a system, a computing system, that you can differentiate it from the general purpose computing by saying it is designed for a specific purpose. This specific purpose can be more than one thing, right? Like, again, in automotive or IoT devices, but it has a specific target at the end, right? And by this definition, we would find embedded systems everywhere, right? Like, think of anything around you, right? In your smart TV, you would have an embedded system. In fact, in your router, like my router has a quad-core embedded system inside it, right? In your gaming console, in manufacturing process, again, we mentioned mobile phones already, in avionics, in automotive, right? Think of any smart homes. Think of anything you would currently, even computer monitors themselves have processors to handle things, right? So when did this start, right? As of 1989, this is 1998, this is the first year that embedded systems already surpassed PC shipping for the first time. This was how many years back? Like 22 years, I guess, right? So since then, the gap between embedded processors shipped and personal computers has been increasing more and more and more, right? So if you think of now, already all PCs in the world are less than 1% of the market. And this might be shocking for some of you. All the laptops around you, all desktops are all less than 1% of the total processing market, right? And then looking forward, by thinking of the IoT revolution and the autonomous car revolution, it's expected that we would have billions of embedded devices everywhere, right? For example, autonomous cars right now already have more than hundreds of microcontrollers or CPUs, or what they call electronic ECUs embedded in the car, right? So let's go a little bit back on the computing system revolution. So starting in 1943, we had this closest computer, right? Think of this was a single computer, in fact, and they took the size of a room, right? And it has very limited functionality, right? And then computers were limited for scientific research use, defense use, and they were very limited. They weren't mass market. Not everyone was able to use computers, right? And then moving forward in the 80s and 90s, we had what we can call the general purpose computer market, where everyone would kind of have access in one way or other to a desktop or a laptop, right? And then in early 2000s, we started having smartphones. This would be the second wave in computing systems, right? So where you have a complete computing system in your hand, rather than previously, the best thing you would aim for is just a laptop that you can carry with you, right? And then 10 years later, we started hearing about wearables, smartwatches for healthcare purposes, or even for fitness purposes. And now, and in the near future, we would have a kind of a more consolidating, bigger market like automotive and IoT or smart homes, right? So this, if we look into this as the journey of computing systems, and we think of it in this way, we find ourselves, in fact, moving to the world of what we call cyber physical systems on a chip, right? Previously here, we had manufactured processors, like if I guess you're not old enough to know about like Intel 86, for example, but I have used one of these myself. So so it's basically a processor that is with very limited functionality, but it was for general purpose use, right? And this is what we used to have in our desktops and laptops. But moving forward, starting from mobile phones, we have what we call systems on chip, where you have in the same chip, not just a CPU, but you have a CPU, maybe a GPU, even ASIC design, specialized processors, or what we call application-specific processors. And those are getting smaller and smaller. So they are embedded first on the phone, then in the wearables, and then they would be everywhere, right? So the near future is we are moving from this general purpose computing thing into what we call cyber physical systems on a chip. Good. So taking two examples from here, so look into the IoT case, right? This is an example of a smart home, but you can think of this as also a manufacturing plant, right? Where you have many cameras and sensors around your home or in the factory. And then there is a centralized processing unit where it collects all this data into a certain hub, do some processing. It has to be very quick with timing guarantees. And then you take an action based on the measurements you have taken. For example, if you are in a manufacturing plant, you measure the temperature of a certain machine, the speed of the machine, usually the health status of the machine, and then every, I don't know, 1 millisecond, 10 millisecond, you take an action whether, for example, if the machine gets too hot or you surpass a certain threshold, you have to slow down the machine, something like that. So it's always a continuous cycle between the physical world and what we call the cyber world or the computing world. And this is the main reason for the name cyber physical systems, right? You have a cyber side, which is the processor that is handling the computation, which is now a system on a chip, and the physical world, where first you sense this physical world, and then you actuate the physical world by taking an action. Okay? So the automotive case is exactly the same thing. Now we hear about Tesla system on a chip, NVIDIA automotive system on a chip. So usually what people are looking at sensors everywhere in the car, cameras, the same thing, and then some accelerators at the edge to run some preliminary machine learning algorithms. And then everything is being sent to a centralized hub or a system on a chip where it takes the final action, maybe synchronize with other cars, synchronize with the server, make sure that everything is okay. Hopefully in the future, we synchronize even with the traffic lights, right? Good. Is there any question? Is there any comment? Okay. So going back to some kind of details, cyber physical systems is the integration of the computation with the physical process world, right? You still build on top of the embedded computing systems, but the first most important thing or principle in cyber physical systems is that there is an interaction with the physical environment, right? And then it also, CBS promotes interaction and the integration of subsystems. So a CBS in general is a system of systems, right? So you have multiple systems. Like if you go back to the automotive domain here, in fact, you can think of any sensor and its associated accelerator as a subsystem, right? But at the end, everything being integrated into a bigger system, which is the control of your car, right? Exactly the same thing for manufacturing plant, smart home, your mobile phone. So you have systems of systems, right? And then the main goal of a cyber physical system is to co-design the cyber and the physical part to make sure that you achieve the system goal, right? And we will see some of the system goals later in the lecture. Some other examples to the ones that I already mentioned about cyber physical systems in healthcare. This is one of the biggest domains where you have cyber physical systems, and there is a revolution going on there right now where you have, I guess, mainly led by biomedical engineering field. Automotive is one example that we already discussed. Here you have smart infrastructure or smart cities where everything is being synchronized together. Manufacturing plants, robotics, avionics, where you have many processing elements. So these are some of the examples we will be touching upon during the course. Can someone add any other system that you can think of as an example of a cyber physical system that we didn't say? Nope. Okay. Good. So the main feature of all of these systems is you sense the physical world through some sensors. You communicate the sensed data to a processing element where you do some computation, and then at the end, you actuate the physical world. So these are the four components of any cyber physical system. In a car, you sense pedestrian, other cars, traffic lights, streets in general. You communicate this to the processors in the car. You compute certain elements using, for example, machine learning algorithms. And then at the end, you actuate by, for example, stopping the car, triggering some alert to the driver or taking action yourself if it's a self-driving car. So some other applications, several new applications are in fact only possible because of cyber physical systems. We already mentioned smart cities, but if you think even in power engineering, we have smart power grids, right? In a smart power grid, which is very common in power engineering right now, you predict and respond to varying conditions of the supply and demand of the power. Previously, it was a fixed rate. And I guess even until now, what you guys get charged with at your houses and the same as mine is, for example, during the day, you have a certain charge, during the night, you have another charge, but it's kind of fixed rate, right? So smart power grid, what they aim for is with the help of cyber physical systems, is they sense and predict the behavior of users. And then based on this, they adapt the cost is one thing, but also there are incentives to users, and then collect some historical data to take some actions, see the places where you can improve your network and grid. So smart power grid is enabling many advances in the power delivery to end users. And another example would be, for example, think of this is a traditional operating room in a hospital where you have many devices around there, many screens, and it sounds like very messy, right? By having like a cyber physical system revolution there, you would basically looking for a very, very clean operating room, clean in a sense that you don't have these so many devices. Everything would be consolidated into a single cyber physical system where it might interact with the server using an IoT device, for example, and then you have a centralized view of the operating room. And taking this further, if you heard about these things, people are talking about virtual operating room where if you don't need the doctor to be there, or a robot can do the operation for you with the help of a remote doctor, which might seem like a science fiction now, but more or less people are trying to get there, right? Good. So we discussed a lot of cyber physical systems, but what are the requirements? So why these are special systems? Why, for example, we don't use the traditional computing systems and cyber physical systems and we are done, right? That's because cyber physical systems have their own requirements that didn't exist in general computing systems. One requirement is, for example, safety, right? Given that you are interacting with the physical world, all the examples we have given, automotive, medical, or healthcare, manufacturing process, all of these things have a safety factor there that you have to meet, right? And if there is, how to define safety? The safety is defined as what would be the consequences if you have a system failure, right? So if the system is very susceptible to these consequences, for example, there would be catastrophic consequences if you have a system failure. This is considered a safety critical system. For example, like an atomic plant, right? Or a nuclear plant, or a smart grid to some extent, an operating room, or a car, right? Where you can even have life losses, right? Performance is another factor. Safety is very important, that's correct, but safety can also be considered as, it was a requirement for very traditional small embedded systems like microcontrollers, right? But now what is different from traditional embedded systems is that in cyber physical systems, you also have a very high performance demand, right? In automotive, you would require to run machine learning algorithms on terabytes of data every second, right? And for this to happen, you have to have a very high performance system, which didn't exist traditionally in, I don't know, like 8-bit microcontrollers, right? And then the other thing is interoperability, which means, assume, for example, you have this system of system. Again, I will take automotive as an example because this is something that I'm pretty aware of. There is no one single company that manufactures everything, right? You have multiple, what we call OEMs, or multiple operational manufacturers, where every company is responsible for manufacturing a certain part of the system. And like as an end company, or like as someone who is just putting everything together, you want to make sure that whatever component you get is just, you can plug and play. Go back again to the concept we mentioned about system of systems, right? You cannot just design everything at once. So you have to have a modular design where every system is designed on its own, then you can integrate everything together. And that's in fact one of the biggest challenges we have in CBS that didn't exist in computing systems. So to achieve all these targets, we argue that we need predictable, secure, and verified cyber physical systems, right? So let's see one by one, what do we mean by predictable cyber physical systems? Take the automotive as another example that we keep discussing. So think of, for example, the airbag control unit, right? So you have, in our cars, we have an ECU or an airbag control unit, which is responsible for opening the airbag if there's a problem. So airbag control unit, you can think of this as a periodic task from a real-time perspective, where it gets activated every 1 millisecond, 2 milliseconds, whatever, right? And then if this task is basically, what does this ECU do is, like, it has a sensor, so it senses the physical world. If there is no crash, you are good. If there is a crash, you have to take an action and open or actuate the physical world by opening the airbag to save the driver, right? If all of this is achieved within the timing assigned to this task, then that's great. So what would happen if crash happens, ECU would detect this, open in the right time, and then the driver is safe. But on the other hand, if you exceed the time of the dictated one by the manufacturer, the airbag wouldn't open in the correct time and the driver is killed, right? So you might have a life loss if you don't adhere to the timing requirements of the airbag control unit. So when we say a predictable cyber physical system, we mean you can predict by a certain level of assurance that you meet the timing requirements. Otherwise, there are severe consequences. Good. So this is a predictable part in the course title. Is there any question? So it's tough to keep talking to the screen, right? So I just need your help here. Right? So if you guys have any comment or any question, feel free to jump in, because otherwise I don't like it to be one way, right? Especially this is a grad course. At least to make sure you guys still hear me, right?
Yes, no question now.
Okay, that's good. So it's like handshaking, right? Make sure that everything is okay. Good. Okay, good.
Thank you. The whole presentation has been good for now.
Okay, perfect. Thanks.
Thank you.
Okay, so we went through this, and then let's see what industry says, right? Given that some of you with some industry experience, so in automotive, predictability is a big factor right now for self-driving cars, for example. Like up until recent years, and this is a slide from a company called AI Motive that is working on self-driving cars. So previously in our regular cars, I don't have a self-driving car, so I just have a Honda Civic. So it's basically looking into this, you have a small number of sensors. So you have small inputs, small networks. You are really not connected to the previous, like the outside wallet. So you don't have Wi-Fi connection, for example. You have a radio connection. You have a small shortwave networks, but you don't have connectivity like network. Some would have GPS, for example. Some would be connected to the internet, but in general, you have small network. And then there is almost no limited real-time use cases. Why we say this? Because in our regular cars, everything is on the driver, right? And the liability is fully on the driver. So you wouldn't expect your car to stop if there is a pedestrian that is going on, right? Or if it's red light, the car would stop from its own. So right now, our regular cars or traditional cars, every liability is on the driver to take the right action. That's why it's very limited in real-time requirements. Yes, the airbag control, the example that I gave, is one thing that would require real-time capability, but how many of these you would have in your car? Yes, you have airbag control. You can think of cruise control as another example, but we don't have many of these. On the other hand, think of the self-driving car. You have tons of data, image and video processing online. You have to do this every millisecond. You have very deep networks. When we say very deep networks, you have connectivity with the sensor network in your car. You might get connected with other cars, with a server, and with traffic lights, with a smart infrastructure. So there are many networks that you get connected to. One of them is the internet for sure. And then we have many and many processing units that would require safe and real-time embedded applications, right? So we are moving from traditional cars into self-driving cars, and this cannot be done without the real-time guarantees. When we say real-time, we mean the predictability that I was mentioning, which is you have to make sure that your system not only is functioning correctly, but also its function happens within a specific time period. Otherwise, it doesn't matter. In the previous example, the airbag did open, in fact, right? So the function was still correct, but it did open late. So it had no effect at all because the driver already lost his life, right? So it's not, compare this to the traditional computing systems where there are no real-time guarantees in my laptop right now, or even using Zoom, right? So we might lose some packets, so you'd require high performance or bandwidth. But if you hear me, if my voice get cut for 1 millisecond or 2 milliseconds, not a big deal, right? So there are no severe consequences for losing timing requirements. These are called generally soft real-time requirement systems. But for automotive or the airbag control example we gave, by only missing the timing requirements for just a millisecond, you might have a life loss, right? And this is the big difference between cyber physical systems with timing requirements and traditional computing systems. So in the other example for IoT, smart home, what I'm trying to do here is basically, and this is my general theme in the course, is give you the concept and look into what industry is saying of how this really applies to the use case, right? So from the IoT infrastructure, also this saying that, and this is from Global Foundries. Global Foundries is one of the big manufacturers of silicon, right? So you have real-time requirements in IoT because you want to make sure you sense the data in the correct time, right? If there is a fire at your home, you wouldn't wait for 10 minutes before you start your fire drill, right? Okay, so we have been arguing a lot about cyber physical systems, but we still didn't say why do we need systems on a chip for cyber physical systems. So CBSOCs is cyber physical systems on a chip, right? So why do we have systems on a chip or general purpose computer architecture for cyber physical systems? The first thing is the challenges we have discussed earlier for cyber-physical systems, safety, performance, interoperability, would enforce you to have these systems on a chip. For example, for performance, now, as we said, we have computation and data-intensive applications. So unlike traditional real-time embedded systems, like the smaller microcontrollers courses that you might have covered in your undergrad, advances in cyber-physical systems would require significant computational power. Think of the F-22 fighter. You would have 1.7 million lines of code, right? In a Boeing 787, you have 6.5 million lines of code. You might expect that a car would have less, right? But in fact, it's not the case. In an S-Class Mercedes-Benz car, you have around 20 million lines of code. And this is not even a smart, like a self-driving car, right? So think of how would be computationally intensive and data-intensive a self-driving car that would require a very high-performance system on a chip, right? So computation and data intensity is one drive or one challenge that we need systems on a chip for, right? So the second reason why we need systems on a chip is we have what we call mixed criticality nature of cyber physical systems. What we mean, take the automotive as also the example we are going through in this lecture. So traditionally, if you develop, and maybe all of you went through this in your undergrad microcontroller course or embedded system course, is you develop like a very small system where you have a microcontroller controlling a critical task, like a pacemaker or a fire alarm or something like this, right? So this is an isolated system, right? A pacemaker, for example, is a very common example for an embedded system that is isolated because it's only on the heart of the patient, right? But in automotive, on the other hand, it's no longer isolated, right? It has many networks, as we have seen, right? So and the second thing is you execute tasks with different criticalities, right? On your car, you would have, for example, high critical tasks like the airbag control example we give, the anti-lock braking system, ABS, engine control unit. All of these are high critical tasks, right? Would require certain guarantees. Otherwise, you have a failure in your car and you might lose your life, right? But on the same time, on the same car, you would also have medium criticality tasks, tasks that would require some performance guarantees, but not as strict as an airbag control. Think of the navigation system, for example, instrument cluster, cruise control. It would require some guarantees, but it's not as tight as the airbag, right? And then finally, you also have low critical tasks where they only require high performance or high bandwidth. They don't have any timing requirements, like the air conditioning unit, right? I mean, if the air conditioning is broken in your car, you will still be able to drive it safely, right? Hopefully, I mean, unless you are driving in 60 degrees or minus 40, right? And then connectivity box, the same thing. Infotainment unit, your radio or your Wi-Fi or your USB connection, all these things are low criticality because really their functioning is not affecting the safety of the car, right? The problem here that is different from general systems or general embedded systems or general computing systems is on the same system, which is your car right now, you have multiple tasks and everyone has its own criticality, right? So we call this mixed criticality systems. And your centralized unit need to handle all of that correctly, right? Otherwise, you would have an operation problem. Going back to industry to see how mixed criticality is affecting different industries, this is a slide from ARM, and they state clearly that you need to enable a mixed safety critical systems for future self-driving cars, right? And I just here quote what they say: increased need for performance and mixed criticality as we move from assisted to autonomous driving systems, right? Another example is from Synopsys, and they state clearly for automotive, you would have key requirements for automotive where you have functional safety tasks, the ones that we called highest critical tasks. You would also require reliability, and reliability is a requirement for medium critical tasks, but also for the non-critical tasks, you would require quality of service or high performance, right? This is from NetSpeed, another company for autonomous vehicles. They also say you have a range of requirements going from excluding performance requirements up to ultra high safety requirements. So maybe here I kind of ask you a question to make sure you guys are following. So this is a terminology from industry. How we map the three types of tasks we mentioned in previous slides, like the lowest critical, medium critical, and highest critical, into these categories. Which one you would think is the highest critical, which one is the medium critical, and which one is the least critical?
I can go for this one. I think is a exploded performance requirement. Maybe this is a lower critical task. And the real-time processing for sensor, this is the medium critical one, and the ultra-high safety and reliability, this is the highest critical.
Exactly. Yeah. Thank you. So it's like you go in this this range or this direction, you move more towards from lower critical to higher critical. And maybe some of you can say it's still a gray area, so it's very hard to decide whether a task is critical or not critical, right? And this is even itself is an active research area where whether a task is really a medium critical or high critical or less critical, but think of the consequences, right? I guess we have a question here, so go ahead, John.
Yes, I'm actually it goes back to what you just mentioned. How would you know exactly which task would be more critical? Because in my opinion, real-time processing of sensors, if you don't process the data in the right timing, it's never going to go to the computer and you'll never do what you want.
Perfect. Yeah, this is exactly.
So in my opinion, it's very critical. But that's one thing I was just wondering. How do you assess this criticality?
Thank you. So as I said, this is an active research area, and for example, in automotive, we have what we call certification authorities, right? So you have to certify a car before you can really sell it on the market. And those certification authorities define different levels. For example, we have ASIL A, B, C, D, E, based on which task is at which level. And you can certify like a system in different level based on the importance of this platform or this system. But maybe you take this as a general rule. It might not be 100% detailed or accurate, but it's generally correct, which is think of the consequences of the task. If it has severe consequences, and severe means might be life losses, then it's a high critical task, like the highest critical one. If it really has only convenience consequences, like for example, infotainment unit, then it's less critical. Going back to your example of real-time processing of sensors, that's correct. Putting all sensors in the same bucket is not a correct thing. It depends really on the sensor and what the action that will stem from this sensed data. For example, if this sensor is, I would say, is for detecting whether there's a pedestrian or a car crash in front of you, this would be of the highest criticality. Or again, like the airbag is another example. But if this sensor is only sensing the health of your wheel according to like a certain metric, then you might still be able to drive to a mechanic, right? So it's not that it's medium criticality, for example. So it depends on the application, because sensors in general are completely different from each other. So it's based on what you sense and what action you take based on this sensing. Does this make sense to you, John?
Yes, thank you very much for answering.
Thanks. So another example from ARM, yeah.
But I have a question here, like
go ahead, Mom.
Thinking about something. So this means like not everything. I mean, it's just only the scenarios like they were thinking about are covered in these standards, right? So for example, I mean, maybe there is like a scenario didn't happen or no one think about it, so it's not covered, right? So is that true?
Yeah, okay, that's an excellent question. It might be a little bit out of scope, but that's an excellent question. So I would phrase that question in the following format: how you can certify something unless you know all the possible scenarios in the real life, right?
Yes, exactly.
Yes, that's correct. So, and this is one of the problems self-driving car manufacturers are facing right now, is how to convince certification authorities that under certain like in normal conditions or even severe conditions, but in real life, like in daily life conditions, you would have at least covered most of the cases with a certain percentage error. It doesn't have to be 100% coverage, but there is a room for error. For example, if you can guarantee me up to a percentage of error of 10 to the minus 15, that in this scenario you would behave correctly based on a certain static proof, as we will see like throughout the course, by doing static analysis or by doing comprehensive experiments, that you are safe under this condition, then I'm going to buy this from you, right? So what certification authorities does, and in fact, this is for automotive, for trains, for avionics, anything that would require certification, they have specific requirements. You would say, you have to guarantee me that under these conditions, up to a certain error, you would behave correctly, right? All scenario coverage in self-driving cars, it's a problem that is not 100% solved yet, right? People are trying different metrics because you will never be able to predict all possible scenarios, right? Many things can come up, right? Good.
Yeah, I see. Because like I remembered like a story related, like someone was ordering by his car like an ice cream, and it was like, once it's a vanilla, the time it takes the car to restart again the engine was different than if he ordered chocolate ice cream. So I just like something like this, it will not come to our minds, for example, into the certification, for example. So what I'm trying to say, so like scenarios like this, how you put them, how you put them in the both ways, in the criticality itself, like how you'll put this, for example, what I said for the ice cream story, in the criticality system, and for example, in if it's will guarantee the safety. So how we'll handle both of them. I mean, it's just like in my mind how this will be handled.
Yeah, so again, like scenario coverage is also embedded in the certification scenarios. As I said, certification of self-driving cars is not yet a finalized field. And this is one reason why we don't find self-driving cars 100% on the streets right now, right? But the thing is, they are still under experiment to make sure at least they can guarantee certain assurance, right? And we will come in the course. This is one of the topics we cover in this course, how to do system verification and to up to a certain metric, or how to make sure you have scenario coverage similar to what you were discussing, right? So it's still a kind of an open problem that wouldn't be easy to answer in a single statement, right? The more we move in the course, the more we will find answers to this question.
Okay, I see. Thank you.
Thank you.
I have also another question, Doctor.
Yeah, go ahead.
So regarding the cyber physical system, we have been said that the main difference between the embedded system and cyber physical system is interaction with the outside or the physical world. Is it like detecting the system failure itself, like a part of the system has a failure? Is this a part of the cyber physical system job, or?
That's an excellent question. Yes. So a good cyber physical system would have what we call reliability metrics there to make sure that you can really, it's called fault tolerance in cyber physical systems, or reliability, right? So what most, for example, think of trains, right? Or cars again. If there is an accident or there is a failure, you should be able to detect this failure as early as possible and take predefined actions based on the type of the failure. So yes, failure tolerance or fault tolerance should be an embedded factor of the cyber physical system. Yeah.
Okay, thank you.
Thank you. And I guess also we are going through this in one of the lectures, so that's a good question. If it's not this one, I guess maybe it's the second one. Okay, so now we discuss these challenges. Let's see why systems on a chip is a solution, or at least people are arguing both in industry and research that system on a chip is a solution for these challenges of cyber physical systems. So what are systems on a chip? Looking here into the left, a system on a chip abstractly is you have multiple processing elements. BE is a processing element. Those processing elements can be CPUs, GPUs, FPGAs, ASIC, security processors, application-specific processors, DSPs, whatever you think of as a processing unit. It can be any of this or a mix of all of them. And then all of them are connected through a network. And then they have some on-a-chip memory and off-a-chip memory. and then also some IOs. This is a general form of a system on a chip or multiple processor system on a chip. Why MBSoC is relevant for cyber physical systems applications? First, because it has a lower cost than other things. One of the main reasons why you are able to buy phones in the price you buy them. And in fact, some phones are even stronger than servers that were there 5 years ago or 10 years ago. One reason why you are able to buy them in the cost that they have is because they have systems on a chip, multiple processor system on a chip. It reduces the cost a lot. Then at the same time, it provides very high performance because one of these processing elements can be a performance-oriented processor, right? For example, in your phone, I might expect that you would have one of the highest ARM processors and then another lower low performance ARM processor for critical tasks. And then also it's energy efficient because each processor can be specialized to achieve a certain task. Again, if you target high performance, one processor can achieve this task, but if you target security applications, another specified processor can do that for you, so you can optimize for energy. And the last thing, and it might be one of the most interesting ones about SoC, it has a very low time to market. What we mean by this? Think of, and those who are working in industry like Synopsys, Intel, Cadence, they will know this. Right now, chip manufacturers don't manufacture everything from scratch. And in fact, they almost never do that, right? It's rarely that they do that. So for example, when I was at Intel, 40% of the IBs are really not Intel IBs. They are just licensed, right? Think of, for example, Qualcomm. Qualcomm licensed processors from ARM. So you get the IB from a third party. And then you build the system on a chip on top of that, right? So by doing this, you lower your time to market to like, for example, 6 months or 8 months. So this is another reason why you are able to find a new phone every year, for example. So they don't design it from scratch. They just kind of plug and play multiple IBs based on the market that they target. Compare this to what we had like 10 years ago when Intel comes up with a new processor. This is a completely different processor than the previous one, right? So you have to go through a very long design and verification cycle to be able to have a new product to the market. SoCs, you have a very low time to market because most of the time you license some of these IBs from other companies. You don't design them internally. Right? So this is for SoCs. What about heterogeneous SoCs? But before this, let's bring another kind of quote here from Hennessy and Patterson from their Turing lecture. So Hennessy and Patterson, for those who doesn't know them, so those are like the top 2 guys in computer architecture. Like it's not one, it's like the most famous book in computer architecture, which is Computer Architecture, A Quantitative Approach. It's authored by them. And they got awarded the Turing Award in 2019. So this part is from their lecture. And basically here they argue that application-specific processors are in fact the future for computer architecture. And the main reason is they call it domain-specific architectures. It's the same thing, domain-specific architecture or application-specific processors. You tailor your architecture to a specific domain. You target automotive, then you tailor your processor with certain features to target the automotive domain. You target mobile phones, then for example, you care about battery life more, then you tailor your processor for that. You target IoT device, so you look for low cost, again, you tailor your processor for that. So it's no longer that you design a processor like Intel and it works for every market, right? And this is one main reason why people are expecting Intel not to win in this new computing systems paradigm, right? Because the way they use to design processors is completely different. Right? Is there any question or someone wants to add anything? I guess Synopsys, for example, is one of the big manufacturers of application-specific processors, especially for automotive and IoT.
Yep.
Okay, good.
Yeah, I wanted to make sure something like, isn't Apple like they change their architecture each year or not?
Which
I'm
one?
talking about Apple. I think Apple, they are changing the architecture.
Apple originally, they in fact, they don't design the architecture. They were either using Intel, but now they are moving from Intel to ARM. But now they want to move to design their own stuff. So in fact, they don't change the architecture, but they might, as I was saying here, they might be licensing new IPs, right? From different markets. Like instead of having a certain ARM processor, you have a different one or a new one, or you put two processors instead of one, right? So you don't change your mobile phone architecture completely, but you change the bigger system, right? So you place different things in different places.
Okay, I see. Yeah.
Okay.
Sorry, so what is
Yeah,
IP?
go ahead. Sorry, go ahead. What is an IP? Yeah, so IP refers to something you can license from another company, right? And this is a terminology used mainly by chip manufacturers. For example, here, if I'm designing one of these systems, I might need to have a CPU processing element, a GPU, an FPGA, for example, all in the same system, an ASIC design processor. So assume now me and you open a company and we want to manufacture a system on a chip. What we can do, in fact, is we can license a CPU from ARM, because ARM business model is that they license their ARM processors, right? License means they give us the design and we give them some cost, right? And then I can license the GPU from NVIDIA, for example, or AMD. And then I can license my FPGA from Intel Altera or Xilinx. And then finally, I can license my application-specific DSP from Synopsys. So as you can see, I can bring all processing elements from different places. And then maybe in our company, we put everything together for a system on a chip, and we target a certain market, like automotive or IoT. So every one of these is called an IP, because IP is referring to intellectual property, and generally it's used for something that you license from someone else. Does this answer your question?
Okay. Thank you.
Yeah.
Yes, thank you so much.
Doctor, I have a question here. So,
yeah.
So what we are saying now, it means like I will use like some processors or some implementation from other companies and use them into my own final design, for example, right?
Correct.
Okay, so now this will be, I was thinking about this, but this may be like, not the best solution. What I mean, like I will not use all the functionality in these processors, for example. So what I mean, it will not be specific for my application at the end. It's still general, right? It's still like general purpose processor, for example, not for specific task which I will use into my design. That's what I was thinking about. Is that
okay?
Not?
Yeah, that's also a good point. So two things here. The first one is those companies, they're like those who are adopting this business model where they license IPs. They usually come up with processors for different markets. Again, Synopsys, Cadence, ARM, are even Mentor Graphics. Like those are like some of the most famous ones for licensing IPs. What they do to make sure they address the point that you say is they have different IPs for different common applications. Like for example, automotive, IoT, avionics, healthcare, these kind of things. So this is the first thing. The second thing is by licensing the IP, you can still internally tune the IP. Like I take the IP design, but I can take one extra cycle to say, I'm going to tailor it a little bit to fit a certain thing. For example, there's a feature that I don't want, then I'm going to disable because it can save me some energy, right? So you have the option either to license it, use it as is, or license it and then try to tailor it to further fit your case, right? But it's still, as far as it seems, it's one of the most successful business models of systems on a chip. This is much better than just developing everything from the beginning. Because the problem is, if you say, okay, I'm going to design it from scratch, you would take at least 2 years. You would just miss the market, right?
Yeah, I see. Okay.
Thank you. Okay, so we discussed systems on a chip or multiple processor system on a chip. So, but when the way I presented it to you, maybe you didn't notice this, but I discussed what we call heterogeneous systems, right? Because I said a processor can be a CPU, a GPU, or multiple of these. So this is called generally a heterogeneous system on a chip. Heterogeneous means it have different features. Every component would achieve different target, right? Heterogeneous systems are very appealing to cyber physical systems for the reasons we will see right now, right? So one thing is, remember we said a main feature of cyber physical system, it has this mixed criticality in nature, right? Which is there are different types of tasks. Each task has its own requirement. This wouldn't be possible to achieve in a system without having this heterogeneity, right? Go back to what we thought of. You have a non-critical task with very high performance requirements, a medium criticality task with some performance and some timing guarantees requirements, and a safety critical task that would for sure require strict guarantees. With a heterogeneous system, what I can do is I can say, I'm going to allocate a high performance CPU or even a GPU to run those tasks that are non-critical, but would require a very high bandwidth, for example. While, for example, for the critical ones, I would even design my system on the FPGA or even have an ASIC specifically designed for the critical ones, right? So now by heterogeneity, you can map different tasks or task criticalities into different processing elements to achieve the targets, right? So the point now is this heterogeneity best suits the MCS conflicting requirements or the mixed criticality system conflicting requirements. Is this point clear? Because this is one of the most important points in architectures for cyber physical systems. You have different requirements from one side. To be able to achieve this, you have heterogeneity in the other side. And heterogeneity means different processors have their own capabilities that can meet one of the requirements of different task levels, right? Okay. So again, from industry, so I would start from the left upright. So this is from ARM. They say, again, for automotive systems on a chip with heterogeneity, you would meet different requirements of different tasks, right? And then for, this is from Synopsys, automotive applications would require different SoC architectures, which means heterogeneous ones. And if you look into one of these architectures, some of them are tailored for infotainment, some are for high-end, like car self-driving tasks, and then MCUs for safety critical ones. And then this one, I believe, is from NetSpeed. They also say you need to translate the system level requirements of a task into system on a chip level requirements, ranging from performance up to ultra high safety critical ones. And then finally, this one is from, if I remember correctly, it's from ARM, and they say clearly that you need heterogeneous computing to achieve different requirements from tasks like image acquisition, feedback action, pattern recognition, and you move from a CPU to a GPU based on which requirements you would address. Good. And then this is another example from ARM. They're saying how different ARM IBs would target different requirements using heterogeneity. For example, computation automation is very high performance. So you would use one of the high performance Cortex-A processors. While if you look for actuation, like the airbag control, you would use some of the most critical, predictable ARM processors like Cortex Real-Time, Cortex R series, or Cortex Microcontroller, which is Cortex M series, right? So you have different IBs targeting different task levels, leveraging the system on a chip heterogeneity, right? Okay. So all of this is from automotive. What about IoT? Again, IoT system on chip is very important. And then they say clearly that integration is key for the low cost of IoT devices. And by this integration, you need heterogeneous system on chip. So you have to put everything together in a single chip solution such that you lower your cost of the IoT device as much as you can. Good. Okay. So here.
Sorry,
yeah.
Doctor.
Go ahead, Salah.
So what is the difference between heterogeneous network or system and cyber physical systems? What is that? Is by default any cyber physical system include a heterogeneous computing, or
okay?
What is the difference?
Yeah, that's a good question. So cyber physical, when we say cyber physical system, we mean the system as a whole, right? We don't refer to any specific platform, right? So cyber physical system is any system that deals with the physical world and has a computation or cyber nature, right? How do you implement this? It's completely up to you. We didn't touch on how to implement cyber physical systems. So the cyber physical system is a domain on its own. When we come to heterogeneous systems on a chip, on the other hand, a heterogeneous system on a chip is a platform type, right? So now we are saying from one side, you have a system that you want to implement. A heterogeneous system on a chip is the best platform to implement this cyber physical system, right? So maybe by giving a practical example, you would think of these things. For example, automotive self-driving cars can be considered as a cyber physical system, right?
Okay.
The best way to handle different requirements of automotive is to have a heterogeneous system on a chip to handle different tasks, right? So a heterogeneous system on a chip is basically a platform you place in your car to achieve the requirements of the cyber physical system. Good. So heterogeneous SoC is the platform, is the hardware, while a cyber physical system is generally the concept of the system itself, right?
So this means that in case if we have like different requirement in the same system, like in the cyber physical system, maybe we need to select a specific processor or hardware for a certain piece of functionality, and another piece of functionality we use another hardware. This means heterogeneous computing, that we have different requirement served by different hardware.
Yes, exactly correct. Yes. And just to make it also clear the distinction between both, you might have a cyber physical system that is not implemented using a heterogeneous SoC. It can be implemented using a symmetric processor system, like not heterogeneous. For example, a system on a chip that has all same types of cores, right?
Okay.
So the system itself is different from how you implement it, right? So, but generally you are correct. The point I'm arguing about here is heterogeneous system on a chip is the best platform that can achieve the requirements of modern cyber physical systems, right? Good.
Okay.
Thank you. Okay, so here's some examples from some further examples from industry that has heterogeneous system on a chip with some real-time processing. For example, from Xilinx, we have one of the most famous automotive platforms or system on a chip, the UltraScale. The UltraScale system on a chip, where it has some ARM Cortex A53, it's called application processor. This is for very high performance. You also have the ARM Cortex R, which is a real-time core. You have a graphics GPU, it's ARM Mali, and then you have an FPGA, you have power management, and it's also certified, right? So this is an example of a heterogeneous system on a chip that is targeted towards automotive, that has different capabilities based on, or different cores to target different requirements from automotive domain. Right? And this is another example from Renesas, where they have their own. Renesas is another Taiwanian company that is targeting automotive. Again, they have a real-time domain for critical tasks like airbag control, and they have application domain for very high performance tasks, like, for example, machine learning processing. Okay, so far. So is there any question so far? I guess there is something on the chat. Oh, thanks, Zen. So is there any question you guys have so far? Okay, so given all this kind of introduction, I guess this is something that comes as nature right now. Like, cyber physical system is a multidisciplinary approach by nature, right? You need to have knowledge, or you need to have team members of different knowledge in different fields. For example, in ECE, cyber physical system design requires that you know some sort of computer architecture, because we are talking about systems on a chip here, processor design. You also need to know about CAD and embedded design. You need to know about software engineering, because what kind of applications you are running to achieve the cyber physical system. We talked about machine learning algorithms, image recognition, sensor processing. You need to know a lot about control systems, because I gave the example of airbag control, ECUs in a car. So you need to know a lot about control. Formal verification is a big factor, because we discussed, for example, how to certify a car or like a healthcare device. You need to know how to formalize your scenarios. And then you need also real-time analysis or scheduling. We will touch a lot about this now. And then, and this is plus other things. Like, for example, if you are targeting a CBS for automotive, you have to have some knowledge of mechanical engineering, might be. If you're targeting healthcare, you need some biomedical or medical information. So there are other fields also that might interact with CBS. What is the problem? The problem is that all such fields and subfields, they are very different, right? They have their own conventions, different developments, right? And this makes CBS as one of the hardest topics to cover in undergrad. This might be, you might even not hear about this topic in your undergrad courses, right? And in fact, I guess 5 years ago, if I'm not mistaken, ECM and IEEE led a kind of an initiative to say we might need to introduce cyber physical system as a track for engineering students. Like, for example, you get a degree in ECE or a degree in like computer engineering, electrical engineering, biomedical engineering. You also get a degree in cyber physical system design engineering, right? But this didn't go through as far as I recall. So we went into some of these challenges as an abstracted way, but maybe now it's the time to go through some of the details. Like one of the challenges, again, safety, as we discussed, but let's see why safety is a challenge, right? In cyber physical system, we mentioned you have an interconnected and interdependent system where, for example, in your car, you are connected with the network. In IoT, you are connected to the internet or your internal network. In a healthcare, you are connected to the healthcare system in the hospital. So there is always this sort of connection in the cyber, or connectivity in the cyber physical system. The problem with this is you cannot trust communication channels by definition, right? Internet is non-secure, right? So for example, if you have a medical plug and play initiative that was proposed, it's still in fact proposed in the biomedical field right now, is for example, you have like a medical plug and play device where the doctor can just take this sensor device and then place it in the whole system and use it. For example, using virtual operation, the example we give, using wireless technology, it's not secure. And for sure, how you can make sure that there is nobody jamming your signal, right? I guess, I don't know if you guys have seen this, but there was this paper in 2018, and there was a video about it. In fact, is you know, you can wirelessly close and open your car using your key, right? It's this wireless key close and open of all modern cars, right? Researchers in 2018 or 17, if I remember correctly, were able to hack into the signal between your key and the car lock itself, such that later, after you close your car, they are able to regenerate the same signal and open the car without a need for a key. There is a very famous video for this. I can share with you on Avenue, right? So again, you can jam the signal given that you have connectivity, which puts your system in risk. The second thing is, once you have multiple users, you cannot trust users, right? Because users, for sure, if they are part of the system, they are not reliable. And it's shown scientifically that, in fact, humans are prone to human errors by nature, right? And one study finds that 90% of avionic accidents are, in fact, happens because of the flight crew, right? And I'm sure that the same thing completely applies to automotive domain, for example. And that means you need to protect your system against user mistake, right? And which is very hard to do. The third thing is, once you have mixed criticality like nature, where you have critical tasks and non-critical tasks, you cannot trust the less critical task, right? Again, another example from automotive domain, I believe I have this example later in slides. There was this very famous like hack of the Jeep Cherokee on the highway, where the researchers were able to hack into the radio unit in the car. And then by doing this, radio is non-secure, right? Because it's connected, right? While your engine control is secure. But the problem in the car is engine control and radio are all in the same system. Again, a cyber physical system with mixed criticality nature. So once the researchers were able to hack into the radio unit, using the CAN network, they hacked into the supposedly secured ECU control of the engine, and they were able to close the car on the highway, right? Which is very, very risky, right? And there is a paper published about this in I guess Black Hat Symposium for Security. So why did this happen? Because of the mixed criticality nature of the cyber physical system. There is a secure element, an unsecure element. Even if you do top security guarantees for the secure one, if you are connected with an uncritical or non-secure element, you lose these guarantees, right? The same thing for if you have a medical pacemaker, where you have a life critical functionality, for example, the one that controls the basing or the wiring with the battery of the car, but also you have non-critical functionalities. Like for example, if you have logging mechanism, or if you have a portal to program the pacemaker, or you have RF communication with the outside world so that the doctor can check the status of the pacemaker. The problem is those non-critical functionalities can be used with a non-normal user or a hacker or someone to hack into the life critical ones. And this would be a very big problem. So what we need to do to achieve safety in cyber physical systems is to make sure we protect the life critical functionalities from the non-critical functionalities, right? And as we would see later, and in the papers that you guys are going to read, this is a big problem, in fact, in cyber physical systems. Great, so these are 3 challenges to achieve safety. So how do we achieve safety then? We achieve safety by verification, right? So the first thing is, can we do formal verification? What is meant by formal verification, for those who are not aware? You basically build a model of your system, a very detailed model, and you have a mathematical proof that your system model satisfies some safety property, right? Can someone see a problem with that? Is this doable, like, or not doable, or what do you think of this? Like, can we use formal verification to really guarantee that safety is met in one of the examples of the cyber physical systems we give? Like, think, for example, of automotive.
I don't think so, because like we said that even the user, we can't like guarantee the safety for the user faults, right? So I don't think so. Like we can come with a formal verification for the safety, because we are not sure what the user may happen. For example, he may, for example, while driving the car, he is drunk, and like he is in a mountain, so he is driving so speed in a high speed. So we can't guarantee these things, I think. I'm not sure.
Yeah, so this might be one possible thing, but let's say we take the input variability away. Assume, for example, the system is standalone. So it's a completely self-driving car. So there is no user here, right? Okay. So would it still be possible? Assume that I took this user part away, or the human part of the system away. Am I able to formally verify like a cyber physical system, for example, like a car?
I think by time, yeah, we can like reach a formal verification to make sure this is like safe enough for using the car. So I think, yeah, it can be valid.
So is there someone else who wants to add anything?
I think modeling the safety property itself is like challenging to because it's related to it need to be tested, not verified using a simulation tools or something. I think it need to be tested in the field.
Anyone else wants to add anything?
Okay, why I will try to validate why I said it can be valid. For example, we build a model for different things, and then as Salah said, it can be tested in the field, and then we can manufacture them, and after that maybe there is an issue with these things, so we will improve these issues. So it's just like a loop. So for example, at the end, we can guarantee this will satisfy like the user, for example. That's what I'm trying to say.
Okay. So yeah, okay, great. So let's take the car as an example, right? What I'm requiring here to achieve this formal verification, I want to have a detailed model of all the car on the same model, right? Which means you have to come up with a mathematical modeling of your car, including every possible sensor you have, every possible camera you have, every possible processing element, wheels, engine, behavior, everything, right? I can really have a model for a simple system, right? For example, here, this might be a model for like the one we have in the right here. It might be a kind of a simple model for the pacemaker, right? Pacemaker is a very simple task, right? But the car, given that this is a very big system like that, it's almost impossible to build a formal model, mathematically proven model for that, right? One reason is, as you said, the input variability from the user, but even putting this aside, given the complexity of the system, and the complexity of most modern cyber physical systems, it's almost impossible to model this mathematically, right? It would take almost forever, right? To make sure that your model is in fact accurate from one sense. And the second thing is it's really comprehensive, that you didn't forget anything, right? The third thing that Salah mentioned is, once you have this model, assume hypothetically we had it, but if you have this model, how even to model the safety property itself, right? You would still need to formally define how your safety is and what are the different conditions. And given that you have almost infinite scenarios in the real life, especially for self-driving cars or avionics, that means you're not almost sure under any condition that you can satisfy the safety property across all scenarios, because scenarios are infinite, right? So the mathematical formal verification of a model is possible only if your model is simple, right? But in a complex system that interacts with real life in a way like avionics or automotive or IoT, it's almost impossible, right? And this is why this path, no one's taking it right now to get a car certified, right? Because it's basically no way you can do this in a time-effective and manpower way. The other direction would be, okay, instead of having a formal model, I would have what we call certification process. And this is what is followed by modern systems, right? It's a process-based mechanism. And I guess this is what Salah was referring to as like, you test in the field under certain conditions, and then you get the certification. This is not formal verification. Formal verification, you don't even need to run any test. By paper and pen, you have a proof and you are done, right? Certification is the other way around, is you need to show that you have run enough experiments in real field and your error is within a certain metric, right? And we have certification standards both for avionic and for automotive, and even in fact IEC is for general electronics, right? Like those who are manufacturing IBs for certain fields like Synopsys, Cadence, Mentor Graphics, they usually go through one of these standards, right? And this usually includes very extensive testing, right? So think of self-driving cars. They have done hundreds, maybe thousands of hours of training, and they're not done yet, right? So it's very, very expensive process. Good. So what we aim for here to achieve safety is verification in a certain sense, whether this is formal verification or simulation-based validation or certification. Why verification is very important to achieve this is, think of some unverified cyber physical systems. One example is, it's a very famous example from Mercedes-Benz. So in 1997, there is a very famous easy test from automotive domains called Moose test. So basically the main point is you want to see how quickly your car can stop if a moose like walks in front of the car. It's called Moose test. It's like a kind of a funny name, but the main point is how fast your car can react to accidental actions, right? So think of if you're driving through like a highway in a forest or in a natural place, and then a moose walks by and it's like very slow. You have to stop as fast as you can. But if you are driving at 120 kilometers per hour, it's very hard to stop instantaneously, right? So the test is called Moose test because of that. But the main point is how fast you can, or how quickly you can stop, right? And most cars pass this test easily. The problem is that, in fact, Mercedes-Benz Class A 1997, which is back then one of the highly regarded cars, failed this test, right? Failed this test. And one other problem this car had is they had sensors on top of the roof just to make sure that if you have an accident and then the car flips, the door will open, because if the door remains closed and then you are not able to open the door, you will be killed, or the car might explode and the driver is inside. So the doors will open by default to make sure that the driver can escape, right? But they didn't take into account that, in fact, a thief would just like very easily, you park your car, you close it, a thief just jumps on top of the car roof to emulate as if you have an accident, and then the car door would open and then the thief would steal it, right? So this is a very funny, it's an extreme example of system that is not verified, taking into account all possible scenarios, right? Another example is for F-22. There was this in 2007, 12 F-22s, American ones, like they were going from Hawaii to Japan. And once they cross the international date line, you know that after, like, why there is this basically like last time on Earth, which is I guess after us with 8 hours, after EST with 8 hours. Once you cross this line, the international date line, all these 12 F-22s, they experienced crashes, multiple crashes. The system stopped, right? There was no navigation, no fuel subsystem, limited communication. They kept rebooting, nothing worked, right? Can someone imagine what was the problem with these like very, very complicated systems, like those F-22 12 Raptors? What would be the problem? Can you imagine?
Time synchronization problem?
Exactly. Like all the systems were programmed using a certain time. Like you have a certain clock. Everything is synchronized according to a certain clock. But once you switch it, like you cross the IDL, your timing systems are completely different, right? Because maybe, for example, you move to another day, either like the coming day or the day before, which based on which direction you are passing from. And once this happened, everything that is based on the synchronization, which is in fact everything, just stopped, right? It's a very, very minor error that would have been handled by taking a single condition line of code among the millions and millions of lines of code in this complex systems, right? So again, another example of how not too well verifying the system can result in a very, very severe consequences. Right? Okay, so the second challenge we had, which is interoperability, or what here I'm calling integration, is now you have different IBs, you have many systems that work together, but you want to put everything on the same system. Again, CBS is a system of systems, right? Let me see. Okay, so we are 1 hour and a half. I guess you guys need a break. Do you feel disconnected? Who is in favor in a break? Like if someone wants a break, can you raise hand? And then I will count the hands. We can take 5-minute break, for example, or 10-minute break, just to refresh your minds. I know I have been talking for a long time. I see here, Salah, Zen, Muhammad, someone else. We have 3. Okay, Miji as well. Okay, so what we can do is we'll take 5-minute break, and then we will come. I would say, let's get it like 8 minutes, and then we'll come 3:45. Okay. Good.
Okay, thank you.
Okay, thank you.
Thank you.